Okay, so calculating delta G when we're not given the delta H value, the delta S value, we have to derive those first. So step one is calculate our delta H. We're going to do that by a Hess's cycle. So to do the Hess's cycle, the top equation is going to be this equation. The equation that I'm trying to find out the enthalpy change for.
And that is formation, correct? No? And what we're finding from that?
Okay.
I'm splashing over myself.
So I've got methane reacting with my steam, giving me carbon monoxide and hydrogen. Okay, so I have been given formation data, enthalpy of formation data, so that means at the bottom I need to put my elements, because remember your definition for the enthalpy of formation is when 1 mole of a substance is produced from its elements in their standard states under standard conditions. So these elements, pick my elements out, I've got carbon and I've got hydrogen and I've got oxygen. If you want to balance that, you need 3 hydrogens and half an oxygen. Okay, so then because it's formation, our arrows go up, formation up. Okay, so on the left hand side, what I have is I'm going to have the enthalpy of formation of methane, and I'm going to have the enthalpy of formation of water. And there's only 1 mole of each, so I don't have to times that by 2 or anything. Then over on the right hand side, I just have the enthalpy of formation of carbon monoxide.
Yes, I'm sorry, I can't do it. It's alright,
You can see even from the table that the value of the enthalpy of formation of hydrogen is 0, because we don't need to include it for an element. The enthalpy of formation of an element is always going to be 0. Thinking about your definition. Okay, if you want to write your values on the Hess cycle, that can be helpful. So the enthalpy of formation of methane is -75. Enthalpy of formation of steam is -242. Just getting these values from the table. And the enthalpy of formation of carbon monoxide is -111. Okay, so next step is to work this out by Hess's law. So we'll label this as delta H1, the left hand arrow is delta H2, and the right hand as delta H3. Okay, so we have the values for delta H2 and delta H3 so far. So let's...
You're doing well so far.
So let's do those, calculate those first. So delta H2 is the enthalpy of formation of methane plus the enthalpy of formation of water, which is -75 plus -242, which works out as -317. Delta H3 is the enthalpy of formation of carbon monoxide, which is -111. Okay, now to work out delta H1, I use Hess's law, which tells me that the enthalpy change is independent of the route taken, provided the initial and final conditions are the same. So I'm trying to go this way, from methane and steam to carbon monoxide and hydrogen. Okay, so am I going against or in the direction of delta H2? Against, so it's going to be what? Minus delta H2, and then am I going against or in the direction of delta H3?
With.
Pardon?
With.
You're going with it? Yep, so it's going to be plus delta H3. Subbing in our values for delta H2 and delta H3, we've got -317 plus -111, which works out as 317 -111, which should be 206 kilojoules per mole. But what am I forgetting? My plus sign. Okay, so step 1 is complete. We have our delta H value for our equation. And now we would need to work out our delta S value. So this is step 2. Step 2 is calculate delta S and convert to kilojoules per mole per Kelvin. Okay, and we were practicing this earlier, it's no different. Okay, so first of all, I want to work out the entropy of my reactants. What are my reactants?
Carbon, CH4 and H2.
Do we know what CH4 is?
Methane.
Methane. Okay, great. How many moles of it do I have?
1.
So I only need to do 1 times my entropy of methane plus 1 times my entropy of water. Sub in those values, should be 186.2 plus 188.7, which is 374.9. Then let's work out the entropy of our reactants. Oh no, our products, sorry. Okay, what are our products?
Carbon monoxide and hydrogen.
Carbon monoxide. How many moles of it do I have?
You know.
1, so I only need 1 times my entropy. But how many moles of hydrogen do I have? 3. So I need to do 3 times my entropy of hydrogen. So if it has a balancing number, you need to multiply that by your entropy to get to your value. Okay, so that's going to be 197.6 for carbon monoxide plus 3 times 130.6 for hydrogen, which gives you a total of 589.4. Okay, how do I then work out my entropy change? How do I work out my entropy change? How do I work out my entropy change?
The sum of them.
The sum of what?
Products minus reactants.
Products minus reactants, great. So the enthalpy of my products minus the entropy of my reactants. Okay, so that's going to be 589.4 minus 374.9, which equals 214.5. And what are my units of this so far? No. Joules per mole per Kelvin. What do I need to convert it to?
Can you do JK?
Pardon?
Can you do JK minus 1 mole?
Yes. Yeah, you can do joules per Kelvin per mole, that's fine. Okay, what do I need to convert that? What do I need to convert it into? Kilojoules per moles per Kelvin. How do I do that? Divide by 1,000. So dividing 214.5 by 1,000, I get 0.2145 kilojoules per mole per Kelvin. Okay, so I now have my delta H value and my delta S value, and all I need to do now is sub that into my equation for delta G, and I will find my Gibbs free energy change. Okay, so step 3. Step 3 is calculate delta G. Okay, what's my equation for delta G? T delta S, great. So my enthalpy value from up there is plus 206 minus temperature I get from my question, which is here, 1200 Kelvin. So go back down here. So it's 1200 times by my entropy, which is 0.2145. Multiply that out. At 206 minus oh, I didn't multiply that out. Am I working out? 257.4. Yeah? Which gives me minus 51.4. What are my units? Kilojoules per
So how do you
mole.
lose the Kelvin?
I'll come back to that in a second. What does this value of delta G tell us?
Feasible.
Good. Why?
That's spontaneous. It's a negative value.
Because it's negative. Good.
That's what it is.
Is the value for entropy, is it a plus?
Yes, you're right. We'll add that plus in. Shows that yes, I told you this 100 times earlier and then I haven't done it myself. If your entropy change is positive, you need to put the positive sign in. Voila. So the last thing we need to look at is determining the temperature at which a reaction becomes feasible or the temperature at which it stops being feasible. Okay. When is a reaction feasible?
When the delta G is negative.
Okay. When, great, and that's what we're writing in here. For a reaction to be feasible, delta G must be less than 0. Okay. Now, since delta G is delta H minus T delta S, that means that delta H minus T delta S must be less than 0. Does that make sense?
Yeah.
So because delta G has to be less than 0, and because delta G is delta H minus T delta S, then that must be less than 0 also. Okay? We'll stick with that maybe and do our example, and then I'll come back to part 2 there. Okay? So, what it says here, this example that we've got is asking for the previous question that we just did. What is the minimum temperature required for the reaction to be feasible? Okay? So what I'm saying is that delta G must be less than 0. Therefore, delta H minus T delta S must be less than 0. Once I've got to that stage, I just substitute in my values that I worked out for delta H and delta S, which were...
Even though we less than, you just make that equal to
No.
It has to be there, it has to be negative.
Okay, delta H we worked out in the previous question was plus 206 kilojoules per mole. And delta S was plus 0.2145 kilojoules per mole per Kelvin. Okay? Yeah. Okay, so substitute those into my equation here. So delta H is 206 minus T 0.2145 for my delta S value. All of that has to be less than 0. When I multiply that out, I get 206 minus 0.2145 T has to be less than 0. Okay, this is where the fact that we have less than or a greater than symbol gets a wee bit tricky, but yeah, what you need to do is what we're going to do is move this to the other side and make it positive and keep the sign the direction that it is. Okay, if you start taking the 206 the other side and divide it by a minus number, that really affects the direction of the sign. So you have to follow through this way. I'll show you. Yeah. Okay. So when I bring that to the other side, it becomes 206. I keep the less than symbol in the same direction, is less than 0.2145 T. Okay. Then to work out what 1 T is, I have to do T, and again keeping the less than symbol the same way around. It's going to be 206 divided by 0.2145 therefore t is greater than 960. Okay, you'll notice that t is on the right hand side and it doesn't look great that way. But what I need to do, you can see right now, if we're thinking back to the crocodile, let's zoom in that. If we're thinking to the crocodile is eating the tea, okay, and it still wants to eat the tea, but it looks a bit more normal.
Does it really matter now?
In a second it will matter. If we write, that means that the temperature has to be greater than 960 degrees Kelvin. I flipped that round, but I've kept the crocodile still eating the temperature. Is that okay?
Yeah.
Okay, so that means that the minimum temperature for this reaction is 960 degrees Kelvin.
Will not be if it was equal to or greater than?
No, but it'd be like 960.
I know, it would be 0 recurrent 1.
Yeah, so, and if you substitute some values into your equation, so say you substituted 900, you should find that it's not feasible. Turns out as a positive delta G value, and if you substitute in 1000 kelvins, it should come out as a negative delta G value. So you can use that to check in your exam. Do a value, plug in a value that's slightly less and one that's slightly more, and check that it works with your feasibility. Okay, so the last thing then, just to make a note of that, sometimes you'll be asked to work out the temperature at which it stops becoming feasible, which is just the other way around. So when is a reaction not feasible?
Delta G is greater than 0.
Yeah, so when delta G is positive, so that means delta G is greater than 0. So this is back up at point 2 here. So that means because delta G is equal to delta H minus T delta S, that means it becomes not feasible when delta H minus T delta S is greater than 0. And you just do exactly the same process but using a greater than sign rather than a less than sign. So just be careful in your calculation when you're doing this. Keep the less than sign or the greater than sign, keep it the same direction and just move your values.
But why would you flip it